Okay, so in this video clip, we're going to take a look at the Vino Verde dataset. This is quite a prominent, sort of celebrated dataset. We see it a lot in the Kaggle kernels and in other portals. And we're going to focus on the red wine bit, and we're going to use machine learning to try and make predictions about the quality of this wine, this Portuguese wine. There are some links here where we can retrieve the data. So the URL that you might go to look at the wine is provided here, and we import it in using the pandas library. If we want to look at the top 10 wines, so each observation here, each row represents a wine. And then it's ranking or quality, which goes from 0 to 10. And then in a laboratory, each of the features were recorded. So alcohol, sulfates, pH, density, fixed acidity, all those features are recorded in a lab. But then a human sensory taste measure is recorded as well. And we're going to use machine learning to see how we can link these features to this dependent variable, right? So some description of the qualities. The alcohol is like a percentage of the wine, percentage of alcohol in the wine. The volatile acidity is linked to the vinegar taste. The higher this is, the more unpleasant wine is, or generally we consider the wine to be less pleasant. The sulfates is a wine additive that contributes to sulfur dioxide levels. We have citric acid acts as a preservative to increase acidity. Total sulfur dioxide density, which is correlated with sweetness. Chlorides, which is the amount of salt. Fixed acidity, acidity, and then free sulfur dioxide and residual sugar. 45 grams per liter is wines that breach that criteria tend to be regarded as being sweet. So if we run just basically a DF shape, we get the dimensions of the data set. The data set we're referring to is DF. We should remember that. So DF here denotes the data that we pulled in. We've called it DF for the purposes of this Google Colab. And then we use these Python commands then coming in again from the pandas just to pull off what information do we have relating to the data set. So what we observe is there are no null values. All the cells are populated with values. So it's a pristine data set. That's one of the attractions of this data set. And they're all, we can see, I think they're numerical values. If we look at them, the float or integer, okay, that's fine. If we do some basic descriptive statistics, then we can see that the quality, the maximum in terms of the quality was 8, but the minimum was 3. So we don't have a 0, 1, 2, and we don't have a 9 and 10. And the mean value is 5.63. And we can, when we compare the mean across the range here, you can see there's quite a variation. So we'll have to standardize these values later on. We'll have to scale them so that we have better, when we don't want a particular column gobbling up the explanatory power. And we have to, typically when we scale, we try to, that the data is converted so that the means are within a range and the standard deviation within a range, right? We'll see that later when we're mounting or setting up the machine learning algorithms using sklearn libraries. Okay, so we need to, our matplotlib Seaborn, which is, we're also going to be using, it piggybacks on the matplotlib, and the NumPy also is useful for mathematical operations. If we look at the unique values, again, there is no 0, 1, or 2, 9, 10. They don't appear. The others do. If you want to kind of get a sense of how popular each quality is, there's a few that hit 8. Quite a few more get a 7. but then the bulk are 5 and 6, and then the low quality wines, then not so many either. The 3 they're a bit of an outlier. The 4, not that prominent. It's the 5 and the 6. It's this medium type wine that is that kind of has the lion's share. But we're ultimately going to convert these values of quality to zeros and ones, 1 being good, and values in excess of 7 or equal to 7 or above we'll consider to be good. That's just an arbitrary break off. So this is a machine learning problem, but it's a classification problem. And it's a bit like other classification problems like the Titanic. Okay, so we get the distribution then. We can see the bulk here is the 5 and the 6s. There's a few who are 8s, and then down at the 3, they're outliers. We could look at the quality of the wine, set up a loop, and then look at the quality and compare it to the pH and compare it to the density and so on. So we just do a quick look. We tend to observe the fixed acidity is sort of associated. Well, there isn't strong relationship there. It's kind of sort of uniform, not that much variation, but then it's kind of more clear cut. If it's a higher on the 8s here, they tend to be associated with the lower volatile acidity. When we look at the quality and the citric acid tends to be, we see kind of positive relationship between them. Not so clear cut what's going on here with the residual sugar. The chlorides, which is associated with the salt in the wine. There's a sort of negative relationship and so on, right? So not so clear cut. A little bit here, the sulfates, it seems to be positively linked to each other, the quality of the sulfates. So the 8s are commanding typically higher sulfates. Quality and alcohol, there's a link here. Higher alcohol seems to be associated with a higher quality. And then quality and quality is unidimensional, as we might expect, right? If we look at the alcohol and quality, again, represented in bar charts, we put here the quality of the wine. We can look at the amount of alcohol in terms of bar chart. And on average, the higher quality wines, the median alcohol is higher. That's not to say you can't get low alcohol, high quality wines, or very high quality, high alcohol, high quality. In fact, maybe here even the highest might be in here. So again, it's not always completely clear. We could have a look here, the volatile acidity, just to see, get another metric, optic acidity with, okay, and I should have done it this way, volatile acidity. Acidity here, and run that. And yeah, we get a negative relationship. So this is the vinegar taste, and typically we don't have that many. The 8s are associated with this, not associated with this higher volatile acidity. Again, if we run that for a scatter graph, again, on the y-axis, where we go 1 as 3, 4, 5, 6, 7, 8. We don't have intermediate values. They're all on that register of a 3, 4, 5, 6, 7, and 8. That's why they're organized like this. But you can kind of see a negative relationship. If we try to build out a relationship between them, it's negative. If we put in here alcohol, it should be positive. So there would appear at first glance here, when we get involved in the exploratory data analysis, that there are relationships here, and maybe they could be useful for setting out, capturing and making predictions about how the features are linked to the quality. Now, if we look at this for a moment, this correlation matrix, obviously at the diagonal, we're getting 1s. And then the 1s are associated with this light coloring, and then the negative values go very, very dark. So again, if we just look at the volatile acidity, and then we compare to the quality of our wines. So this one here, it is negative 0.39. So it's definitely a negative correlation there between them. But then when we look at the quality, maybe we can make this 15, 10, and 10, just to make it a little bit more compact on the screen. Let's run that. And okay, I think we see everything. So when we look at the quality here, compare, look at the estimate of the correlations, the volatile acidity and quality, they're negatively correlated. When we look at the quality and the alcohol, they seem to have a strong positive correlation. And the next obvious one, well, I suppose it's probably quality and sulfates. And then after that, 0.23 citric acid. So there's some definitely positive correlations, some negative correlations. Again, it's fairly clear that when we compare total sulfur dioxide against free sulfur dioxide, there's a positive relationship. Okay, so this is kind of a preliminary type analysis. We can kind of see some relationship here between the variables, between the quality and the other feature variables. And I suppose at this point then, what we might do is say, okay, let's take the qualities and then in a very arbitrary way, let's say to convert our values into bins so that they're either 0s or 1s, and those values in excess of 6.5 are considered good, and those less than 6.5, so 6 and lower, is bad. Now, this is purely arbitrary because a 6 could actually be quite decent wine, but we're just doing that to give us a starting point and to put a line in the sand, right? And do follow the hyperlinks to some explanation here in terms of this sklearn package, which is a very standard package for implementing machine learning. And it sort of provides us with the wherewithal to do battery of machine learning procedures and then evaluate the performance of our model. Okay, now sklearn is quite a valuable library, and because it provides so many frameworks under the same umbrella, it means that it's a kind of a one-stop shop where we can just mount quite a few machine learning algorithms and then evaluate those. It's a free software machine learning library for Python. In this case, we're going to use it for classification, but also can be used for regression, clustering algorithms, and we can use it for support vector machines. And you can see here we'll have random forest, gradient boosting, and so on, right? So these are all state-of-the-art machine learning algorithms. Let's import them in from the sklearn or the scikit-learn, and just make sure that I organized into bins. Now, did this work? Okay, I'm getting an issue labels. Let's see what the PD cut, where the problem is arising here. Okay, so I ran this again and it works, but we just have to be careful that once I convert to bad and good, I don't go back again and hit again. Otherwise, it's looking for the 2, the 3, the 4, the 5, 6, 7, and 8, but it's not going to find it because here we have the bad and the good. I think we could probably just below here look at maybe quality. Right, just to see what pops up. I did it again. I didn't take my own advice. Okay, so I'll just pause for a second and then come back and clean that up. Okay, so we run that command again. It'll now organize it as bad and good. We could possibly just take a look, Control V and run again, and you'll see when we run the df describe, we're getting, it would have been good and bad and good, right, in terms of what we have here. So that's fine. Let's just remove that and take this one out. Okay, so now we want to Skyness is it's written in Python, uses NumPy extensively for high performance linear algebra and array operations. It was set up in conjunction with Google Summer of Code, which is a project by David Kunapu. And it stems from the notion of a SkyKit, SkyPy toolkit. Okay, so we import those in, and then we have to take our good and bad and set them out as zeros and ones. Okay, so we're going to use a LabelEncoder, which we have here. So we import that in from sklearn.preprocessing. Okay, so let's just run that snippet of code. And then if we take a look then at our df head, we don't have bad and good, we have zeros and ones. And the df head, if you like, if you compare this data set to what we had before, these were both sevens, and now anything above 6.5 is considered to be good or one, right? So now we have a binary classification problem that we're going to solve. And if you look here, the same data set, the first 10 rows, we had 2 sevens here, they're now converted to 1. So otherwise zeros and ones, which are binary values that are now capturing the quality, and we're kind of saying bad wine and good wine, and that's a very arbitrary delineation between the two. Okay, now do follow the hyperlinks. I'll leave in the video clip, I'll leave the link to this Google Colab, which will be up in Vinegar Hill, but I've used heavily these portals for getting snippets of code and combining snippets of code together. And then I followed the Medium, there's an article here, Medium Better Programming, Titanic Survival, and the setup that was used in terms of the training the data. So we want to create a divide our data up so that we're using 80% of our data to train the algorithms that we have in situ, and then 20% of the data which will not be used for training, but for test. And then we've kind of a seed value here, the random state equal to 0. And so what we're setting out is we're going to have the X variables which exclude quality. So everything here except quality is the X, or the independent variables, or the features. And then the Y's, just one Y here, is the quality. Right, so the Y denotes quality, the X's are filtered or siphoned off, and we drop the quality in from the DF dataset, and that's our X. And we're going to use these to try and predict the quality, right? Okay, and then we split our dataset. So once we have our Y and X's siphoned off from each other, we then divide the X's into a train and a test, and the Y's go into a train and a test. And then we also have to scale. We saw before that there was quite a bit of variation in terms of the means and the standard deviations. So we've got to impose, again, this is coming in from the sklearn libraries. We're going to import in StandardScaler. We've already got that imported in, and we apply that scaling. to the features, right? So what follows then is based on this article that I used here. So it might be no harm that you just take a look at the Titanic data set and how we use the machine learning to classify and make predictions about survival and drowning, survival and perishing. So we run a whole battery of machine learning algorithms, and it's actually quite fast, right? Now our data set is not huge, but we have random forests here, we have decision trees, we have Gaussian naive Bayes training, we have two support vector machines, K nearest learning training accuracy and logistic regression. Okay, we're going to run our models here, and then we will have output in terms of accuracy, and they're all doing pretty good. Now, this is within sample, and of course we want to test out of sample, and that's where we need to use the test. So if we train the X's on the Y's and then evaluate the accuracy within sample, of course, we're going to get extremely high estimates of accuracy. We need to obtain those, observe those, how we should evaluate those models in terms of the testing data. And again, we're going to look at these also, but using confusion matrices, where we look at, again, in this lower apex here, we have 12 and 277. So this is the poor wines, the wines 6, 2, 3, 4, 5, and 6, or I think 3, 4, 5, and 6. They're the bulk of the wines. They make up about, if we recall, 60, 70% of the wines. Let's just see. I should have made an estimate of how many fell within. So it might be no harm if we go back and just take a look here at some specific numbers. High accuracy sometimes can be obtained by doing kind of dumb stuff. So let's have a look at this. So if we take remember we have 53. So we have 53 that are, no, we have, in terms of the 7s, there's 199. Plus in the 8s, there's only 18. And the total sample size is equal to 1,599 wines in the total, 1599. So in terms of 13% of the wines we consider to be good. So we should be getting, if we said they were all bad, if our prediction was that they were all bad, then we would be getting 80%, 87, 86% accuracy. So 86% accuracy is what we've got to beat. And perhaps these machine learning algorithms are a little bit too flattering. So what we would try to do is try to predict the good ones, right? It's easy to predict the poor quality wine. It's more onerous, more arduous to try and predict the high quality. That's what we're finding here. A lot of the time we're saying so here we're saying this is actually predicting bad wine and actually bad wine, predicting good wine and actually good wine, right? But then we're predicting, we're saying 18 were good, but they're actually bad, right? And likewise, when we come down here, we've predicted here more correctly 17 that were good. We're getting 91%, and we're getting here 92. These models are quite good. 92, 91, and there, if we can go back and look at the well, the random forest seems to be quite good. And the next best then is the second one down, which I think is not logistic. It is the nearest neighbor training accuracy, right? It's not too bad. So the random forest seems to be standing out, and it seems to be quite good at predicting the good wines, and maybe, but also this one here is getting a lot of the good wines, but then it suffers. It's predicting a lot of, in comparison, let's say to this one, it's predicting a lot of good wine, but then we're missing out on the others. So the confusion matrix here, the random forest, which is the final one here, probably is doing maybe a reasonably good job at picking out the good wines. And that's the tricky bit. Predicting the bad wine, we just need to, if we only want to predict the bad wines, we could say they're all bad and predict that they're all bad. But the tricky bit is predicting the good ones. If we predicted all the wines were bad, we'd actually get a relatively good level of accuracy. And so this is what the confusion matrix reveals here, and it's quite good in terms of getting an overall picture in terms of what's going on. Again, if we're to look here in terms of the headings, we import in the data, we have to use the pandas to get some kind of organization over the data frames. We apply, we inspect the data, we have descriptive statistics, we do visualizations, we set out a correlation matrix, right? We try to see what are the areas that are highly correlated with each other, and then we must classify either as good or bad. We port in the sklearn packages, and then we set out the variables as either being a 0 or 1 using the LabelEncoder. So our variables quality is binary, and we set out then the Y's and the X's. We split train and test. We have to scale the values. We implement the machine learning, and then evaluate the performance in terms of confusion matrices. I would say here the random forest looks a bit better. And again, but we're not improving that much over a kind of blind prediction. Just say they were all bad, right? And we would still have quite a high level of accuracy. So again, the way these machine learning algorithms work, they're a little bit like black boxes. And one of the main benefits of having a black box that's predicting is that predictions can be made quickly. So we get a lot of data, and we control an algorithm that crawls over this, and then it makes a prediction about the quality. And possibly a lot of the time, the prediction is quite good, right? But it automates that process, and it means then we can package it up into an application. And then if we have enormous data sets, then these machine learning algorithms come into their own. So if we have to do some kind of quick delineation between good and bad, the machine learning algorithms, although imperfect, can help us do that. And the more data we can use to train our algorithms, the more accurate these models become. So even though we have 1,599 data points, right, which is clearly a relatively good amount of data, the scale of it is quite small compared to what we might consider big data. Data so big can't fit on a single computer. Okay, let's leave that there.